Achilles, from here you can. Achilles, if from here you can carry on. Okay.
Okay.
So can we start our session?
Yeah, Kritika, go on.
Okay. So good evening, everyone. I am Kritika Jain.
And I am Pavavi. We are thrilled to welcome you to the exciting workshop on drone technology, hosted by the YANTRA Robotics Club of IIT Madras. As a member of this club, we are constantly exploring the cutting-edge technologies like robotics and drones. And today's session is a part of that journey.
Today, we have the honor of learning from Dr. Soumya Ranjan Sahu sir, an associate professor at IIT Kanpur, Department of Electrical Engineering. He completed his BTech at University College of Engineering, Burla, Odisha, and earned his MTech and PhD from IIT Bombay. He is well-published researcher with extensive expertise in drone technology.
Dr. Soumya will be sharing the insight on the latest advancements in drone technology. We will also have a Q&A session at the end, so keep your question ready.
And don't forget that we are having a quiz coming up soon on drone technology, so stay sharp.
Let's give a warm welcome to Dr. Soumya.
Hi, thanks.
Thank you.
So let me know if you can see the presentation.
Yes, sir. It's visible.
Okay, so the first slide is visible, right?
Yes, sir.
Okay, so what I planned today was to give a very basic on what drones are and specifically multicopters, because that is what I've been working on for quite a few time now, and rough idea on how one can go about designing things, and finally I'll not be discussing codes and all, but give you some iterations or architectures that people usually follow to create these drones and make them fly. Okay, so the whole idea is about understanding the technology that has been there, and of course towards the end we'll discuss on what are the advancements that have actually gone into these drones. Okay, so the first thing that we usually ask is, what are drones? Okay, so these are primarily used in conjunction of unmanned aerial vehicles. Now, as the name suggests, it is an unmanned vehicle, which means there is no onboard human who is basically piloting the vehicle, and it's an aerial vehicle, which means it can hover or it can fly. Okay, it depends on the type of the vehicle that we are having. Okay, now why the specific name of drones came up is it was it's a very old term which has come from the classification of bees. So bees, you have a queen bee, a worker bees, and I think there are also a classification which are called as drones, okay, which act on commands. Okay, so from there on, somehow the history says that this is how these unmanned aerial vehicles came to be known as drones. But the term drone is very much used analogously to multicopters. Okay, as opposed to these fixed wing aircrafts and rotary wing aircrafts, which will see soon see the classifications. Okay, now these drones can be autonomous, semi-autonomous, or manual. So when we say they are manual drones, they are basically drones which are completely remotely piloted by humans on ground or humans on any other platform. The human can be present on a moving ground vehicle, it can be present on moving aerial vehicle, and so on. But the point is, this unmanned aerial vehicle, when it is completely remotely piloted by a human, then it is known as a manually operated drone. So all the missions, all the flights, all the path taken are decided by the human, and the commands are just passed on to the drone through remote signals. Okay, radio wave signals. The semi-autonomous is basically those drones or rather autonomous. Let's go to autonomous first. Autonomous are those drones which basically receive mission information from any command center, which can be a ground-based computer or human. Okay. Now, once the mission is received, the drone takes into account the mission parameters and decides the path that it is supposed to follow, the commands that it is supposed to execute, and proceeds with its decision to execute the mission. Okay. So the human is only involved, or the external computer is only involved in giving the mission parameters to the drones. So that is where we call it to be autonomous. Semi-autonomous is somewhere between manual and autonomous, wherein in most cases a human operator or a onboard computer, it not only gives the mission parameters, but also plans the paths that are supposed to be taken, or plans the actions that are supposed to be taken by the drone. And these are the commands that are passed on to the drone, and drone executes these commands, which in turn basically executes the desired mission. Okay, so it is somewhere in between a manual operation, which involves a regular involvement of human, but the human is not piloting this. There is a onboard computer that pilots it, but for piloting you need commands, and the commands are basically given in terms of paths or directions by the human or onboard computer. Okay, so now if we classify drones, those drones are aerial vehicles. Okay, so they need to have some kind of force that actually lifts them up and keeps them afloat in air while they are moving. Okay, so depending on the surface that generates this lift, the force that basically keeps them afloat, we classify them as fixed wing unmanned aerial vehicles, rotary wing unmanned aerial vehicles, and flapping unmanned aerial vehicles. These are the three major classifications that one can see, and there are a lot of vehicles under that you see in these classes. The popular ones, I mean, which are commercially available in fixed wing UAVs, are the General Atomics MQ-9 Reaper. When I say commercially, I mean this is not for public use. This is basically military drone. So General Atomics MQ-9 Reaper that you see on the extreme left is a fixed wing drone. So at the back of it, it has a propeller which is basically used to give a forward thrust to the drone so that it moves forward, and when it moves forward at a certain velocity, because of the wing structures, it generates a lift, and this is the force that keeps it afloat. Okay, so the lift is created because of the wings which are moving at a certain speed in air. Okay, another form of fixed wing UAV is basically an example which I have shown as the AeroVironment RQ-11 Raven UAV. So this UAV is a small fixed wing UAV which can be hand launched. Okay, so the UAV started with the propeller at the highest speed possible, and it is hand launched, meaning someone throws it by holding it in the hand, and that is where from where it can basically take off its flight. Okay, so such hand launched UAVs are usually belly landing. They land on their fuselage or the belly, or at times there are some capture nets on which they can be captured, whereas fixed wing UAVs like these, the MQ-9 Reaper, they are basically something that can be launched from a runway, because they have wheels, something similar to our commercial airplanes that we usually fly. Okay, now the rotary UAVs, sorry, yeah, so the rotary UAVs again have two broad classifications. One is what we call as the helicopters, and one is what is we call as the multi-rotor UAVs. Okay, helicopters are basically autonomous forms of rotary UAVs, where they have a big main rotor, okay, and one tail rotor. So this big main rotor is basically responsible for generating the lift. Now in this case, the rotor, when it starts spinning about the vertical axis at a certain speed, the wings that you see, the blades that you see here, okay, these blades, because of their movement in the air, they will generate lift, and that is how the helicopters will take off. The tail rotor primarily is used for attitude control, so it contributes to some part of the attitude control, but it is the main rotor which is primarily used for all the translational and rotational control of this helicopter, of course along with the tail rotor. Okay, so because this is one single rotor unit, they have a very complex structure of actuation, which is basically called as force plates. And in most of the helicopters, the speed at which this single rotor moves is kept constant, and the pitch angle of the blades are changed so as to achieve different amount of lift or different amount of moments to maintain the vehicle. Okay, the multi-rotor, which you see with some yellow parts attached to it, this is one of the vehicles that we are working on our lab. Here what you see is, unlike the helicopters which has just one single main rotor, it has multiple rotors which are responsible for generating the lift. Okay, so this is a 4-rotor arrangement where in each of the arms there are 2 rotors which are basically put to be coaxial. Okay, it's in a coaxial arrangement. Now these rotors, when they rotate at a certain speed, they generate lift, and that is what basically takes the vehicle up. Now by differentially controlling the speed of the rotors, in such cases you can basically generate forces and moments in different directions so as to control the vehicle. Okay, so this helicopter is basically electric helicopter called as eVibram, which has been developed by Endurair, a startup by one of our IIT aerospace faculty member. And this is something that we have developed in the lab, the quad rotor. Now the one that you see in between, which is labeled as Subble, okay, this is again a product that has been developed by Endurair. You see that it has 2 main rotors now. Okay, so this can also be classified as a multi-rotor UAV, but the actuation system that it has is similar to what the actuation is there on the single rotor of a helicopter. Okay, so it is a kind of hybrid between a helicopter and a multi-rotor, where there are 2 rotors in place, 2 main rotors at 2 ends, and the actuation system is somewhat similar to this helicopters. Okay, so it has no tail rotors in this case, and all the attitude and position are maintained by controlling this particular these 2 rotors. Okay, again in both the cases, the speed of the rotor are kept fixed, whereas the pitch angle of the rotor blades are changed. Okay, now why is that we kept the pitch angle, we change the pitch angle but do not change the speed, is as the force. So these vehicles have, for example, Subble has a all-up weight capability of, I think, 20 to 50 kgs, which is huge. Okay, so which means they need motors which have good inertia, and the propellers are also huge in size. So when you try to change the RPM of such an arrangement, the time taken by the rotor to react is significant. Okay, so the time constant of such a rotor system is significant. You need the time constant to be as low as possible, so the response time is fast, and that is why changing the blade pitch angle through the arrangement of what we call as a force plate essentially has a faster response time, and that is why the speed of these rotors are kept constant, and we focus on changing the blade pitch angles. Whereas quad rotors, which are smaller in size, in such cases the motor propeller system that we have low inertia. Okay, which means if we change the give commands to change the speed of the motor, it can be realized with a very low time constant. Okay, that is why in small quad rotors you would see that the control is mainly by controlling the speed of the motors, whereas in bigger vehicles it is not the speed but rather the pitch angle of the blades that usually changed. Now, unlike fixed wings and rotary wings, where the lifts are being generated by these wings, the flapping wings are something which are basically biomimetic and are mimicking the birds, where the wings basically flap in a certain pattern to generate the lift. Okay. Now the advantage of this is they can attain a good camouflage where you don't want them to be distinguished from different birds, and they are a lot agile and energy efficient, and they can be very light. Okay. The smallest flapping wing UAV that I know of, I think, is known as hummingbird. It actually looks like hummingbird and replicates the motion of how a hummingbird flies. Okay. Now moving forward, now each of these drones to operate needs some energy source. Okay, so it is either based on gas. When I say gas, it is basically gasoline. So it can be petrol. In some cases, people do use hobby fly, uses ethanol and so on. Electric ones primarily rely on battery. These days, there are drone setups where it is a hybrid kind of mechanism wherein it is actually run on fuel. So the fuel runs a electric generator set. So there is a engine that drives a DC generator. This engine basically consumes either ethanol or petrol. Okay, and this DC generator produces the energy that is required to drive the electric motors. Okay, so the actuation system of the drone is actually electric, but the fuel that is being supplied is either petrol or ethanol. So the engine drives the DC generator, and the power produced is used to drive the actuators and other electronics on board. So this is a hybrid system that is actually being used. Okay, so this e-Vibram and the pod rotor that I am showing are basically electric ones. A new type of energy source has come in. So you would have heard about the buzz going around, things turning out to be hydrogen powered. Okay, so these days you have hydrogen powered cars. You would have seen that India is soon going to test hydrogen powered trains. Okay, so there is a company in Netherlands, or rather it is the Netherlands Aerospace Center, which has basically developed in 2019 hydrogen powered drone. Okay, they named it Hydra. So you see the red tank on top. This red tank is essentially the hydrogen tank, and this red tank or the hydrogen tank supplies hydrogen to the fuel cells, and the fuel cells in turn generate electricity, which basically drives all these motors. Okay, so again, this is a form of hybrid where the hydrogen is the fuel and the hydrogen is not being ignited or it not being combusted like you do in a typical IC engine, but rather this hydrogen is being utilized in fuel cells, which eventually generate electricity, and the DC electricity is used to basically run the electronics and the propulsion system on board. Now these are examples that I have shown where these drones basically carry their own source of energy with them. There are drones, so we classify such drones which carry their own source of energy as non-tethered drones. They are not tied to any source on the ground. Okay. Now the limitation of these is, especially those which function on batteries, is their endurance. Okay. If you want higher endurance, you need a bigger battery pack which has a good amount of energy stored in it. But as the battery size increases, the weight of the battery increases, which means the all-up weight of the UAV will also increase. Now, once this all-up weight calculation increases, it means what? That you need to generate more amount of force or more amount of lift to keep the vehicle afloat. Okay, which means you need bigger motors and bigger propellers. Now, once the big motors are big, so the weight of the motor and the weight of the propeller also increases. So it again goes in a loop, and you end up increasing the size of the UAV while trying to increase the endurance. So the endurance increase for it probably I don't know the exact calculations but for some increase in endurance, you have a significant increase in the battery. Okay. This problem can of course be handled by gas powered drones. Okay, and of course by hydrogen drones have not come up yet commercially at large scale, but gas powered drones are of course there. But the problem is these gas powered drones have a good amount of noise signature. So when you do not want noise signature to be significant, you want to have electric powered drones. Okay, and now to counter this endurance problem, what happens at times is for unmanned aerial vehicles which are capable of taking off vertically from a point and landing also vertically down at a point, unlike the fixed wings which basically need to be hand launched or need a runway to take off. Okay, such drones can be tied to a tether, and this tether is basically a power cable along with a data communication cable which is tied to a ground station. So if you can see in this figure, this is a quadrotor which is basically tied to a tether to a ground station. So the ground station supplies all the power to this tether, and the data that is to be transmitted is transmitted from the UAV to the ground station through the tether. So there are two cables that usually runs. One is basically the power cable and another is the data communication cable. The advantage of this is, depending on the continuous operation limit of the actuators and onboard electronics, this tethered vehicle can remain up for a very long time. Okay, so this is primarily used to monitor areas. For example, if you want to monitor huge gatherings, the Coldplay concert is going to come up, right? So if you want to monitor the gathering there, tethered drones are a very good idea. You can launch them to heights up to 100 meters and you can hover there for a long time. You do not have to worry about changing the battery as opposed to a non-tethered drone. Okay. Now, depending on the type of use, we have consumer drones which is for personal use. So you would see a lot of so the Amazon sale is going on now. If you search for this toy drones, they would cost you around something between 1,500 to 3,000 and so on, and it can go all the way up to 60,000-70,000 depending on the features that you're looking for. You can use it for photography, you can use it for recreation and so on. Okay, one of the popular drones that is there in the small form factor is the DJI Phantom Mavic. DJI Mavic. Okay, DJI Phantom is also used for photography and it is a very popular drone. Commercial drones, these drones are primarily for industry application. They're used for surveying, they're used for monitoring, they're used for infrastructure inspections, they're used for business to business delivery or business to customer delivery. So basically point to point delivery of products. And then you have military drones. They are basically drones which are specifically built for armed forces applications, which is surveillance, reconnaissance, and combat. So because of this, they have additional requirements like the components have to be military grade and they have to be stealth. The noise signatures and heat signatures should be low enough so that they cannot be detected and so on. Okay. Because of stringent requirements that comes with the requirement for this military drones, the price of such drones are comparatively very high as compared to commercial drones. And consumer drones, since it is more like a hobby grade thing, so the drones used in commercial, the consumer drones are the cheaper ones that you would usually find. Now, what are the components that usually go on for a drone? Okay, I'll speak mostly with respect to multi-rotor UAVs, but these components are in general true for all kind of UAVs you see, except for the frame that you use and the propulsion system that you use. Most of them, all of them almost, are the same that is used for drones. So the primary components I might have missed out in this list. So as we proceed, we'll see if we have missed out something. The primary components are the frame, which defines the vehicle, whether it's going to be a fixed wing, whether it's going to be a helicopter, whether it's going to be a quad rotor, whether it's going to be a hexacopter. Hexacopter means it has multiple rotors, basically 6 rotors to go on, whether it's going to be flapping wing and so on. So the frame is decided based on the application. If you have long range missions, then people usually go for fixed wings. If you have short range missions or surveillance mission, or you want to basically monitor area or take photographs of some steady objects and all, you can go for this vertical takeoff and landing capability drones, which are basically helicopters and multi-rotor UAVs. Okay. So once you decide the frame, the next thing is to decide the propulsion system. Okay. Of course, for fixed wings, the lift generating factor is the wings itself, but the propulsion is dependent on the rotor, or it can be any other engines. So MQ-9 Reaper uses a rotor mounted on the tail at the extreme end of the UAV. Okay, so that is what essentially propels it forward. In case of helicopters and multi-rotor UAVs, you need a motor propeller combination, which basically is responsible for lifting up the vehicle and maneuvering the vehicle. Now, this rotor system also has something known as an electronic speed controller, which is primarily responsible for controlling the motor and interfacing the motor with the autopilot board. Then you have sensors. Why are these needed? These are needed so as to have information about the vehicle, where the vehicle is, what is the attitude of the vehicle, how fast the vehicle is going, is the vehicle in a flying state or not, and so on. Then you have a telemetry module. Telemetry module is a module which keeps on transmitting data from the vehicle to something known as a ground control station, and getting information or commands from the ground control station to the vehicle itself. Along with that, you have a transmitter receiver set, which is basically the transmitter is always with the pilot, and the receiver is mounted on the drone. Okay. Then you have an autopilot, which is primarily responsible for controlling the drone. You have a companion computer, which is attached to the autopilot and is responsible for taking higher order decisions. And then, of course, the energy source. Okay. So if you see here, if you see this figure, this guy here is the GPS, and this module usually comes along with the magnetometer. We'll see what these are. This is the motor, and the blue ones that you see here, these are the propellers. So this is a tri-blade propeller. People go for 2-blade propellers as well. This, the one that you see written 3DR, this is the telemetry module, which is on the vehicle, and then there is a companion telemetry module on the ground station. This is the autopilot. So this is a Pixhawk board. Then of course you have power modules to power up. The battery is beneath this, and the receiver module is also somewhere beneath this, which is not visible in this particular figure. Okay, so this connector that you see is basically to connect the battery. The battery goes underneath this particular drone, the way the drone has been done. Okay, so these are the primary components that we'll have. So we'll discuss these components next in details. Okay, so the frames that are usually used for multi-rotor UAVs are the most popular one, because they are very cheap. The glass fiber plus polyamide nylon composite. These cost something between 650 to 1,000 rupees. These are composite frames with the mounting plates being basically PCBs, where you can install your ESC, route your ESCs and the battery connections through them. These are lightweights. The figure that I have shown is for a 450 mm frame. Now, when I say 450, it basically from the propeller's motor center to motor center, diagonally opposite. Okay. Then you have carbon fiber composite frames, where the entire body is made of carbon fiber. So here the arms that you see are essentially of carbon fiber, along with the base plates and other mounting plates. They're all carbon fiber made. You have frames which are 3D printed, so the entire frame is 3D printed. So these days, to make drones light, you have 4D printed frames. So when I say 4D printed, what it essentially has is basically you have 3D printed plates. Along with that, there are PCB layers which are also printed. Okay, so you embed the PCB on the frame itself, which becomes one structure. In fact, there is a, I think there is a open source frame design available, which has the entire Autopilot PCB spread out on the frame itself. So it's a small quad rotor frame where the entire surface is used as the PCB. Okay, so the same thing is used to mount all the actuator and other sensors, and the same surface is used as the Autopilot as well. It's one single PCB. The PCB itself acts as the frame. Okay, so the idea of having so if you have frames which are these, it makes things a little heavier. But if you go for one-shot units which are 3D printed with all PCBs embedded, it makes things a little lighter. Okay, and then of course this is one of the vehicles that we had in the lab, which is made of mostly 3D printed parts. Okay, so they are usually composites, or you can basically 3D print using carbon fiber infused filaments. Okay, so you have nylon CF filaments, you have PLA CF filaments, you have I think ABS CF filaments, and you have PETG CF filament. Okay, so with this carbon fiber infused in these filaments, when you 3D print, the strength of the structure basically increases, unlike simple PLA, ABS, PETG or nylon. Okay, so you can 3D print these things as well. Okay, motors and propellers, they are usually dependent on what is your desired all-up weight, the size, the power requirement of the motors, the size of the propellers. They all depend on the all-up weight, because you need to know what is the amount of thrust that you need so as to fly your drones. Okay, the motors that are used in drones are brushless DC motors. Why brushless DC motors? Because these motors run at very high speeds, and these motors are easy to control. You can control their response time is fast. And in brushed motors at very high speeds, the brushes basically wear off. Okay, which is not a problem in brushless DC motors. Okay, now there are two types of brushless DC motors that are used: the outrunners and inrunners. Of these, outrunners are pretty popular, and if you see a motor, usually the motor rating should be based. You would see that there is something known as a kV rating. You would see motors written as 1000 kV or 2200 kV or 480 kV and so on. So that kV rating essentially means how much RPM are you going to get out of the motor for every volt supplied. So 480 kV means it is 480 RPM for every volt that you are going to get. So if you give a 10 volt supply to the motor, it is going to have a RPM of 480. Okay, similarly a 2200 kV motor means is going to have 22,000 RPM for 10 volts supplied to it. Okay, the next thing that you look into when you choose your motor is continuous power rating. Okay, you have peak power rating. So this peak power rating is also associated with that certain amount of time, meaning that it can draw some X kilowatt power only for 5 seconds. Means if you cross that 5 seconds, the motor will burn out. Okay, whereas continuous power rating means it can draw this much kilowatt continuously. Okay, so this is the basically power rating, or this is the current draw that this motor will have without generating much of a heat when the motor is running. Then of course the voltage range, whether this motor can be subjected to a 22 or 24 volt supply, or can be subjected to a 48 volt supply. What is the minimum supply at which it is going to run, whether it is 11.1 volts or whether it is 7 volts and so on. Okay, so the voltage range also becomes important. Propellers, you need these propellers to have strength, because when they move at very high speed, they experience a lot of load. Okay, because these propellers are essentially taking everything up. So all the force is acting on these propellers. Okay, so the material of the propeller have to be strong enough. The popular materials that are used are glass fiber plus nylons. These are very cheap propellers, usually used in hobby grade flights or cheap commercially available drones. But mostly nylon infused carbon fiber propellers are used. And then there are carbon fiber cloths from which the propellers can actually be made using some dyes. Okay, the diameter of the propeller decides decides how much thrust it can generate, because it's something like a wingspan. Okay, longer is the wing, more is the lift that it can generate. But again, longer is the wing, more drag it experiences. So the increase in diameter, the drag experienced by the propeller also increases. Along with this, the pitch angle of the propeller, basically with respect to the rotor plane, by how much angle the propeller blades remain inclined. Okay, that also determines the amount of thrust that it can generate. Higher the pitch, better is the thrust, but beyond a certain value you lose thrust, and it will not be able to generate any thrust beyond a certain angle. So optimally, if you will see that the pitch angle remains somewhere between 4.5 to 6 degrees. And of course, there are this aerofoil structure that also affects the choice of the propellers. Okay, now I'll show you a typical motor rating. Let me see if I, sorry, not this. Yes. This is basically a typical motor rating for this is for a T motor. So if you go to any good motor seller or good motor brand, so this is basically a T motor. This is a Chinese company though. This is a U11 version 2 motor. You would see the CAD drawing, which basically tells you everything about the mounting points of the motor. And this is important when you customize your custom make your own frames. And then when you choose the motor, this is something that you want to look. So when the motor was tested under lab conditions, it was found out that it has around 120 kV rating, which means it is going to give 120 RPM for every volt supplied, and the motor weight is 772 grams. Now this lead that you see, the lead is a 14 AWG wire. So this is talking about the motor terminals, the wire that are acting as the motor terminals. Then the configuration is 12 and 14P. This means that if you have seen motor configurations, you usually have stator poles and rotor poles, okay, or magnetic poles. So 14P means there are 14 magnetic poles or 7 pair of poles, okay, and 12 N, which means there are 12 stator slots. Now typically BLDCs are 3-phase motors, so 12 slots, there are 3 phases, which means 4 slot per phase. Then of course there is a shaft dia. The idle current at 18 volt is 1.5 amperes, which means if you just connect the motor and the motor is not running, it will still draw 1.5 amperes. And the rated voltage is the maximum that you can connect is at 12S LiPo. So 12S LiPo roughly configures to 48 volts, and the peak current that it can draw is 57.3 amperes up to 180 seconds. Okay, 180 seconds is 3 minutes. So up till 3 minutes it can draw 57.3 amperes, beyond which it will burn out. Okay, and the maximum power that it can give is 2783 watts. So this maximum power is again for this 180 seconds. Along with this, you typically see that a motor, the company themselves, they suggest the best possible propeller that can go in. For example, they have tested this motor at 48 volts, and they are testing, the test table that you see is for a T motor carbon fiber propeller, which has a 26-inch dia and 8.5 degree pitch. Okay, So here the pitch is a little large and the dia is big. And then you have the throttle rating. So for example, at 50% throttle, it is able to generate a thrust of 3.5 kgs roughly. Okay. The torque that it is experiencing is 1.09, where you have an efficiency of 9.61. For every watt consumed, it is able to generate 9.6 grams of thrust. So this is what this table essentially helps you in deciding what kind of motor propeller combination you can use. So they have given another also for the same motor at the same voltage for a different propeller. Here the propeller size has increased by 1 inch and the pitch angle has also increased by 0.3 degrees. And again, if you see at 50%, that was giving around 3.6, this is giving around 3.8 kgs of thrust, and the efficiency, but you see, has gone down slightly. So this is something that actually one should actually look into. So usually the manufacturers, if they have their own propellers, well and good. If not, you can basically look into such test tables and figure out what kind of propellers would basically go. The reason being that these are the efficient possible combinations that one has. Okay, this is a exploded view of the same motor that we were discussing. And these are the propellers. So propellers usually, in case of multirotors, the number of counterclockwise propellers are same as the number of clockwise propellers, so as to counter the drag effect that is generated by one propeller with respect to the other. Okay. Now these are interfaced with electronic speed controllers. This is again a T motor example that I have, and the electronic speed controllers have these specifications as shown. Basically, what is the voltage level that can be applied to, whether it has a battery elemented circuit with it or not. So meaning, can you tap 5 volt to 11 volts from it or not? What is the peak current that it can supply and for how much time? So this guy can supply peak current of 60 for only a duration of 10 seconds, beyond which it will burn out, but it can supply a current of 40 amperes continuously. Okay. And then the throttle refresh frequency of 500 hertz with a throttle response speed of 120 milliseconds. If you change the throttle, it takes 120 milliseconds to respond and change the voltage levels that are appearing across the motor. Okay, so typically what you have are these 3 terminals, which are the motor terminals that goes to the motor. This is a heat sink inside which the entire electronics, basically the controller, the gate drivers, and the MOSFETs are there. This cable that you see at the center, this is the signal cable and also the programming cable. And then you have the positive terminal and the negative terminal which get connected to the power source, which is typically a battery. The signal cables get connected to the autopilot, and the autopilot is the one which generates PWM signals. So the PWM signals are something that come into this controller inside, which accordingly drives the MOSFETs to change the voltage profile that appears across these 3 orange LEDs that you see. Okay. Now the sensors that typically go in these are the first one, or the main important one, which you would see invariably in any unmanned vehicle, is the inertial measurement unit. Typically, we use 9 DOF IMUs. Why 9 DOF? So they have a 3 DOF accelerometer, 3 DOF gyro, and 3 DOF magnetometer. Okay. How much time do I have now? Okay.
Sir, you can go ahead. We have enough 1 hour or more.
Okay. So the accelerometer output is usually in terms of G. So 1 G is basically 9.8 meter per second square. And when I say 3 DOF, it means it can measure the acceleration along 3 axes: the x-axis, y-axis, and the z-axis. Okay. Similarly, you have a 3D rate gyro. The 3D rate gyro again gives angular rates along all the 3 axes and usually gives it in terms of revolutions per second. At times, the output is in terms of degrees per second. And then you have a 3-axis magnetometer, which basically calculates, gives you output in terms of degrees with respect to the x, y, and z-axis. Now this sensor is rigidly, this sensor is fixed through a vibration isolation platform onto the vehicle. Okay, so this is fixed so that the measurement, once it is fixed to the vehicle, the measurements that are going to come is always going to be with respect to the vehicle. Okay, so whatever you see is always with respect to the vehicle, and then when we talk of controllers and all, we have to do suitable transmissions, and the output of these are fast. So we sample them at a very high rate. Towards the end, we'll see what are the typical sample rates that we use. So the data can be collected at a very high rate. Okay. Along with this, we use a GPS model. GPS, as you know, is the global positioning system, okay, which gives you absolute position of the vehicle. Now this output is usually in terms of lat and long, so latitude and longitude. But if you want it in terms of meters and all, when the vehicle initiates, the Autopilot software, wherever you start the vehicle and wherever it gets its first GPS fix or the first GPS lock happens, that it puts that latitude and longitude is put as home position, and whenever it starts moving around, from that point it calculates the relative position in terms of meters. Okay, so the point where the first GPS fix happens is known as the home position. From the home position, which becomes the origin now. Okay, so this home position becomes the origin for what we call as the earth fixed frame or the inertial frame. Okay, this is something where the frame is fixed with respect to the earth, and as it moves, you start getting information in terms of meters for the XYZ position. Now, typically, the update rate of GPS are pretty slow. The cheap ones that you see have an update rate of 1 Hertz. Okay, so every 1 second you will get information about the position, and once you get the information about the position, you can also estimate the velocity from these sensors. You have barometer. Barometer, as you know, measures the height measures the pressure difference with respect to the mean sea level, and the output is usually in terms of bar. With the suitable calculation, you can convert this bar to height with respect to the mean sea level. So you get your values in terms of meter. Again, the sampling rates of parameters are comparatively faster. Now these sensors that I mentioned are sensors which do not need a lot of processing. They have small processing units on board, and the output of these can be directly fed to autopilots, which are low level computers. Now the sensors that I will talk of, basically the LiDARs and the cameras, are sensors which need a good amount of processing. Okay, they have a lot of information stored in them, so they need a good amount of processing, and they cannot be processed by the autopilot. So LiDARs, again, they are fixed to the body of the vehicle, and hence all the reading is with respect to the frame associated with the body, the coordinate frame associated with the body. Now there are 3 types of LiDAR. 1D LiDAR, which is basically point LiDAR. It just gives the distance to the object where it hits. Then you have a 2D LiDAR. It basically scans on a plane and generates point clouds on the plane. And then you have 3D LiDAR, which generates point clouds in the 3D space. Okay, so if you see the images taken on the right, this is with respect to the 3D LiDARs that have, you can almost see the 3D structure of the environment. Okay, so they again have a slower rate and they need a good processing power. Another sensor which is very popularly used are cameras. So they can be RGB cameras, they can be infrared, or they can be EOIR cameras. EOIR cameras are popularly used for military applications or any other applications where you need infrared information along with RGB information. So they are used for navigating the drone either manually or autonomously. When you do it manually, you basically see the live stream of the camera and do it. So what you basically see is the first person view, as if you are sitting in the UAV while maneuvering it. So you have FPV cameras which transmit the videos to a remote station from where a pilot controls it. And then of course there are cameras which basically transmit data to an onboard computer that processes it and navigates the vehicle autonomously through the environment. Okay, so this right hand side is a photo of a camera which basically is a EOIR camera. And here on the left hand side bottom, what you see is a camera which is basically a FPV camera. Okay, the first person view camera. Then the next important part is the transmit receive unit. So this is what a pilot typically has. So even if a vehicle flies in autonomous mode, there is always a manual override present, and the pilot is always there with its control units. So as when a UAV has some problem executing some autonomous missions, it can take over the UAV and bring it back home. Okay, and this is the typical receiver unit that is used. I mean, this is what we are using at least in our drones, and has a good range of a few hundred meters for test purposes. Now the main thing that we have is the autopilot, which is the main brain of the unmanned aerial vehicle. It processes all the sensor signals, command signals and messages. It generates the control signals and then transmits the same to the actuators, which essentially are driving the UAVs. Okay. Now these autopilots can be basically just processing boards which gather information from all sensors which are not associated with it, or the autopilot boards like the one that you see here in the figure are the ones which carry sensors on board them. So the sensors are integrated. But camera and LiDAR are something which the data cannot be processed by these. So typical examples are Pixhawk, Pixhawk Q, the one that you see here is the Pixhawk Q. We have a CUAV, you have flight base, CC3D, you have autopilots from DJI and so on. Now to process LiDAR informations or process camera information and run, for example, complicated path planning algorithms, or if you want to run a neural network, then you need something known as a companion computer. These computers are not real-time computers. So autopilots run real-time OS, whereas companion computers need not run real-time OS. They usually run embedded Linux or the usual Linux that we use on our systems, to which these LiDARs and cameras are integrated. And typically they have more processing power as compared to the autopilot. So depending on how much processing you need, you can choose your boards. ARPI 5 is a very popular one because these are cheap, but they have low processing powers, but more enough than the autopilot board. The next one is the Jetson Nano. On top of it, you have Jetson Orin, which has a better processing, and then you have Jetson TX2 boards, which have faster processing and can handle LiDAR data as well. But again, please note that as the processing increases or the computation power increases, the power consumption by such boards also increase. So when you account for your batteries, you not only account for the motors that are going to drive them, but also for the sensors, the computers on board as well. Now with all these sensors and all, before we start building or before we start constructing the controller, we need to model. Okay, so this modeling is usually done on the basis of first principles. These are physics-based models, and for miniature UAVs, we can assume that they are rigid body capable of both translation and rotation while under the effect of gravity. And when we model this, we need to associate frames. So the popular frames that are used, so there are three main frames that are used. The first frame is the earth fixed frame. So there are two types of earth fixed frames that are used. One is a NED frame. So x-axis along the north, y-axis along the east, and the z-axis points down towards the center of the earth. Whereas the other type of earth fixed frame is the ENU frame, which is east means the x-axis, north means the y-axis, and up means the z-axis. The popular choice that is usually used in any of the autopilots is with respect to the NED frame. Okay. Now, this frame is something that is, as I said, it has the origin where the home position is marked, okay, where the first GPS fix is attained. The next frame is a frame which is on the vehicle and is typically said that the coordinate frame has the origin on the center of gravity of the vehicle. This is a frame which remains parallel to the earth fixed frame. So whether you choose a NED or a ENU, it remains parallel to that frame, and that frame is fixed. It's just there. Basically, it's a frame that has the origin at COG. Basically, the NED frame or the ENF frame translated to the vehicle. So this frame keeps on moving with the vehicle, but remains parallel to the earth fixed frame. And then you have a body fixed frame. Now, in this case, in the body fixed frame, typically the forward motion direction of the UAV is considered as the x-axis. If you take the right hand side of the UAV to be the y-axis, then the positive z-axis is vertically down, and vertically down meaning perpendicular to the xy plane of the body. If you take y-axis to be the left of the vehicle, then the positive z-axis is perpendicularly up. It is perpendicular to the xy plane of the body. So the x-axis remains fixed. The x-axis is always in the forward direction of the vehicle. Now, depending on whether you choose the z-axis to be up or down, you will have the y-axis either to be the left or to the right. Similarly, if you choose your y-axis to be right or left, the z-axis will be down or up accordingly. Typically, if you choose a NED frame, you go for a body fixed frame which has the x and the y to the right, x to the forward, y to the right, and z to be perpendicularly down. But if you choose a ENU frame in the earth fixed frame, then you go for the z up configuration in the body fixed frame. Now, why is all this needed? You have this IMUs, you have this LiDARs, you have these cameras all mounted on the body. So the readings come with respect to the body frame. You have GPS, which is mounted on the vehicle, but the readings come in the absolute frame, which is basically the earth fixed frame. So the readings are coming in two different frames. The velocity estimates from GPS come in the earth fixed frame, whereas the velocity estimates and the accelerations estimate from the IMUs come in the body fixed frame. The gravity is acting in the earth fixed frame. So you want to relate all forces and torque together. Okay, so once we have established this notion of frames, what we do is we define the attitude of the vehicle as the orientation difference between the body fixed frame and the vehicle frame. Okay, with this two frames orientation defined with respect to each other, now we can translate or transform forces in one frame to the other frame and write down our force balance equations or moment balance equations. That is what forms the dynamics of the UAV. Okay, so that is why understanding these frames are very essential. Now, the attitude of the vehicle is the main thing. So we either denote it by Euler angles. So in case of UAVs, it is a ZYX rotation that we say from vehicle frame to the body frame, or we denote it through unit quaternions or through rotation matrices. Euler angles have their problems because of singularity at certain configurations. For example, when the vehicle has its nose up, so the forward direction is pointing exactly up. At those points, you cannot distinguish between yaw and roll, which is taken into, which gets taken care of when you use unit quaternions and rotation matrices. And rotation matrices are the ones which do not have any singularity, which means that every rotation matrix depicts a unique orientation between the vehicle frame and the body frame. Okay. So these days you would see controllers coming up with the knowledge of rotation matrices, and to ease things up, people also design controllers using unit quaternions. The Euler angle concept is not being used much, but only is used for flights which are not highly maneuverable. Okay. Now, once you have understood your frames, once you have understood the dynamics, you know your measurements are available. Now you generate your controllers. You generate your control inputs, and please note that these control inputs that you generate are always in the body frame. Why? Because the actuators are fixed to the body. So whatever forces and moments you are talking of are always with respect to the body frame. Okay, so that is why you need to understand this orientation between the vehicle and the body frame. So with suitable transformations, you can write the force balance equations. Now, once you have the physical system and you have come up with the dynamic model using the first principles, now this dynamic model is very complicated. It accounts for every thing that you can have for a UAV, almost everything that you can have for the UAV, but these are very complicated higher order ODEs and they have non-linearities. Okay, so designing controller around these becomes difficult. So what we do is we simplify these models around operating points. For example, let's say a quadrotor is going to move, but it is not highly maneuverable, which means the attitude changes won't be much, which means the attitudes would remain close to, would remain within 0 to let's say 30 degrees for roll, 0 to 30 degrees for pitch, and the yaw angle would not vary much. Usually the nonlinearity comes of the roll and pitch angles. Now, with this, if you assume that these angles are going to be restricted within -30 to +30 and all, then these are basically the small angle approximations that can be used. So sin theta can be approximated as theta, cos theta can be approximated as 1, and so on. So with these approximations, now notice that these approximations are being done about these operating points. You know that the operation range is this, and hence you simplify the model. When you simplify the model, what happens is you end up with lower order differential equations, and in fact in some cases you end up with decoupled equations, which means a big system can now be considered as sets of smaller subsystems. Now with this small subsystem in hand, you design the controllers. Okay. Now what is done is the simplified models are used to design the controller. Once we have designed the controller, we just put it back in the simulation and see whether the simplified model is responding as it is supposed to respond. That's the first step in any control design. Okay. Now once we have a satisfactory response from the simplified model, then we remove the simplified model and go to the detailed simulation model that we had, basically the entire dynamic model that we had, because that represents the physical vehicle. We use the controller and run the simulation with the detailed model and observe the output and tune the controller accordingly. Once the performance is fine, the next step that we go is integrate this control along with the physical system. So the physical system is the hardware, and the controller goes on to the autopilot board as a software. So now here, unlike in the previous two cases where the simplified model and the controller were in the software, or the detailed simulation model and the controller were in the software, here the physical system is the hardware and the controller is the software. So the hardware and software start interacting, and this is where we again do the last tunings for achieving the desired performance. Okay. So this is how a control is designed. Now this control has an architecture to it. Okay. This is what the hierarchy is. You have the physical UAV, which has sensors on board that generates estimates about the state of the vehicle. What is the attitude of the vehicle, where the vehicle is, what is the rate at which the attitude is changing, what is the velocity of the vehicle, where is the vehicle going to head, what is the health of the vehicle, and so on. All these states go on to every stage of the hierarchy. Okay. The UAV is primarily flown by an autopilot. The autopilot essentially generates commands for the actuators, which we call as the servo commands, and these commands basically help in maneuvering the UAV. Now there is a boss that sits on top of the autopilot. So the autopilot, once it generates these commands to the UAV responds, and the state estimator gives the measurements. The autopilot compares these measurements with whatever command it had got and generates errors, which are basically position errors. Okay. So what are the commands that have come to autopilot? The commands are basically what is the altitude, what is the heading that it should maintain, what is the velocity it should maintain, and so on. So the airspeed, altitude, and heading commands are received by the autopilot. So depending on that, it generates servo commands. Once the UAV responds, the state estimator measurements come, autopilot generates and says, hey, this is the position error that I have. Now how much airspeed and altitude and heading have to be corrected. This is what goes to something known as the path following commander. Okay, so this path following commander is responsible for generating this airspeed, altitude, and heading commands. So path following commander, path following module generates commands for autopilot based on the position error information and the path definition. What is path definition? Whether it is going to go in a straight line, whether it's going to take an arc of a circle. If it is an arc of a circle, what is the radius of the arc, and so on. All that information comes to this path following. Basically, it has a path that is commanded to it. It ensures that it generates this velocity, altitude and heading command so that the path is followed. Now, who gives this path information? This is given by path manager. The path manager decides whether it has to move in a straight line or a circle. Okay. Now, this path manager decides this on the basis of the tracking errors that the path following controller is, path following module is generating, and on the basis of the waypoints that the path planner sees. Okay. Waypoints are basically points that are decided by the path planner. What does a path planner do? It sees the destination, it sees the map, and depending on the destination, map and the existing obstacle, it tries to fit in a path so that the UAV can go through different path and attitude, okay, while maintaining different position and attitude, so as to go from a start position to the goal position. So the path planner plans the entire path either with the help of waypoints or with the help of a curve, which eventually goes to the path manager. Path manager tries to fit in all the straight lines and the circles that it can, circular arcs that it can have, which goes to the path following. Path following ensures that the path is being followed by generating commands for the autopilot, and the autopilot sends in the commands through by actuating the actuators that are there on the UAV. Okay, the disturbance that can come in case of a UAV are the winds, because winds are always there. Even if you don't feel it on ground, at a certain height you will have some amount of wind. Now, for miniature unmanned aerial vehicles, a wind speed of 3 to 4 meters per second is also significant wind speed. Okay. Now, this is an architecture that is usually followed when there are no cameras. But if you have a camera for navigation, only the path planner part changes. And now the camera feedback is used as a guidance tool. So whatever you see, you perceive your environment accordingly and plan your path. So the path planner is now replaced by a vision-based guidance. Whatever is the visual feedback, you accordingly plan paths, and the remaining architecture remains the same. Now, before we conclude, I'll just give you an overview of the usual structure that is used in popular autopilots like Pixhawk. So this is a structure that is used. So you get the position set point, which is XSP, and the heading set point, which is PSP. The position set point goes to the position controller, which is basically based out of a proportional controller. So proportional means whatever error is there between the commanded position and the actual position, it generates a reference which is directly proportional to that error, nothing else. So the output of that is a velocity set point. This velocity set point then goes to the velocity controller. Basically, this velocity controller tries to attain this velocity set point. This is a PID based controller. So PID based controller means it has 3 parts to it. One generates control effort proportional to the error. One generates control effort not only proportional to the error but also what has been in the past, and one generates control effort with respect to the rate at which the error is changing. Hence the PIND, proportional, integral and derivative. So the velocity controller eventually generates an acceleration set point, which is ESP. So this acceleration set point and the heading set point, they together go into the attitude command. Okay, these eventually generate the quaternion set point, which is the attitude set point, which goes to the angle control, which is again a P controller that gives me angular rate set point, which is the angular velocity set point, which again goes to the angular rate controller, which is again a PID. So you notice the structure is same here. You have position and then velocity, you have angle and then angular rate control. Finally, you get your actuations, okay, which is basically roll pitch, the moments needed for generating roll pitch yaw and the thrust. And then you have a mixer. What is this mixer? This is basically a control allocator which decides how much changes has to be done in which actuator so as to generate the desired forces and moments. So this is what the desired forces and moments are. Now notice one thing. This is in the inertial frame, the position and velocity controllers, which are running at 50 Hertz. And here the attitude controller are at 250 and 1 kilohertz. Okay, and these are basically something that are calculated in the body frame. So an example of the angular rate loop, you have the set point, you have the actual angular speed. This is basically the derivative controller. This is the proportional part, and this is the integral part, which together go through a saturator to generate the. This is basically for the moments, attitude moments, and similarly for the attitude loop, you have the quaternion set points. You have the desired quaternion, which goes through error quaternion calculation, generates the quaternion error, from where we extract the scalar and the vector part, and depending on the algorithm that we have used, it generates the attitude angular rate control set point. So this omega SP is something that goes in actually here in the angular rate loop. Okay. So the similar structure is actually followed for position and velocity control as well. So you have your desired position compared with actual position, which generates the velocity set point. And the velocity set point compared with the actual velocity gives you the acceleration set points. Okay. Now, so this is all that I have. But just to emphasize on what is new that is happening in such areas is this entire structure that you are seeing. People are of course attempting to realize this using neural networks or deep learning tools. The only problem with deep learning tools or neural networks is whatever you have on board has to have a good computation power. At least that is what I believe. So I think deep learning tools can be very well used for decision making, basically higher order in the architecture, which is path planning and path managing. But we have a lot of established literature with experiments, of course, where they have shown that deep learning can also be used to run low-level controllers, which is this attitude controls and the position control. They're really interesting work. One of them actually demonstrates that a neural network trained racing drone can beat the best possible drone racer, human drone racer in the world. Thank you. I have taken I think around 15 minutes extra, so I'm sorry for that.
No worries, sir. That was an insightful session, and really thank you for that session. It was an amazing session. And sir, now we have some questions.
Yeah.
So can we start that?
Yes, please.
Yeah. So there are some pre-message questions for us, like those who were not able to join this workshop, but they'll see the workshop after this. So can we ask that first?
Yeah, please go ahead.
So the first question is, currently NASA is exploring drone options in planetary missions such as Ingenuity. What do you think is the scope of such application in an Indian context?
I'm not sure how. I'm not sure whether ISRO is exploring such things, but the Ingenuity project is basically, if you see, is based on a helicopter design, to the best of my knowledge. Okay, so what it has demonstrated is for interplanetary, or rather planetary explorations, when you are on the surface of a planet, probably unmanned aerial vehicles based on single rotor designs, which are helicopter, may be a good option. And the reason is such vehicles have a VTOL capability, and you can vertically take off and monitor a larger area as opposed to basically ground vehicle, which basically keeps on moving at a slower pace. So this can give you a bird's eye view, at least up to a certain altitude, and allow you to cover larger areas. I'm not sure whether ISRO is looking into such things as of now or not.
Okay, sir. So there's another question. Drone swarms are currently used by various countries as a means of visual presentation. What do you think of the scope of swarm robotics using drones in other applications? What are the general advantages and limitations?
Okay, so you have bot labs from IIT Delhi, which perform this visual demonstration of swarm of drones, if I'm not wrong, during the Republic Day, I think, retreat celebrations. Okay, you can see the videos, they are there. Okay, so India does have, but now coming to their applications other than this visual representations, They are something I would say they are huge. For example, let's say that I take a drone which can monitor a certain area, but then you want to monitor a larger area and you have a lot of drones, but the limitation is they can fly only to a certain height. So you can use a network of drones to essentially monitor a larger area. Okay, so this is where a swarm can become effective. Swarms can also be used as relay stations. For example, you have a base station on one side of the hill and there is a base station on the other side of the hill. You need to transmit data. Okay, so how do you do it? So basically make 2 or 3 drones fly in a formation at different heights and they can act as your relay stations for you. Okay, you can basically use swarm of drones. So there are reported literature where swarms have been used rather not swarms but multiple drones have been used for load transports, which was not possible with the use of one drone. Okay, so there are applications that you can see. Now what are the challenges that one can foresee is, if you want to achieve what we want to look in as an autonomous swarm, you need inter-drone communication. And as the number increases, you don't want any interference happening when drones are communicating with each other. Then there has to be drones which can communicate to the ground station also. So probably of a swarm of, let's say, 10 drones, there are 2 drones which can communicate to the ground station. So through these 2 drones, you should be able to control all the 10 drones. It's not that you can only communicate to these 2 drones, but you can also communicate to all the 10 drones through these 2 links that you have. The second thing is, the links can break and make depending on the inter-drone distance, because eventually the wireless communication is dependent on how far they are from each other. Okay, and as you move away, the size of the data that can be transmitted, and I think the bandwidth, that is what is called, is it reduces. Okay, so you have to always try to be within optimal range of each other, so that the transmission rate is good enough between the drones. But if it happens that you are experiencing that a link is going to break off, then you should be able to reconnect to another drone so that you be a part of the network. So there are some works which look into this self-healing swarm, which essentially is something of this sort. Okay, in fact, in swarms, what happens is, depending on your algorithms, if one of the drone goes bad, it can drop down the entire swarm. So you should be capable of getting rid of the bad drone from the system and repair your system, swarm system accordingly. Okay, so these are some challenges which people are actually looking into. Yeah.
Okay, sir. So there is another question. Is there any upcoming battery technology which have a better capacity and have a long life maintenance, maintaining the weight and stability for voltage and current?
Battery, I'm not not aware of. Sorry, but as I said, of course, the hydrogen thing is coming up, with the hydrogen tank being on the top and the fuel cells being used as the battery, which which the organization has claimed that has increased the endurance of a typical electric vehicle. So that is one option. But of course, there's some research going on the batteries, but I have really not looked into it, so I cannot answer it.
Okay, sir. Guys, if you have any other question, you can ask. Raise your hand, and then I'll tell you to who will ask first. Okay, you can ask, unknown.
What do we need to do to increase the degree of freedom? Like in that you explained, 3 degree of freedoms are like stable, but there are all another 3, right? The rotation part.
Okay, so see, typically quadrotors are 6 degrees. They have 6 degrees of freedom. Okay, but they are under actuated because the number of actuations that you have is full. So what I think you mean is, how can you have position and attitude to be controlled as you desire, right? So in such cases, you increase the number of actuations, but then the argument can be that hexacopters are examples where you have 6 number of actuators and hence it is a fully actuated system. Well, it's not. You should be able to basically do some thrust vectoring. Okay, so if you look into the literature on tilt pod rotors, that is an example of thrust vectoring where you can move the rotors. So you can change the rotor plane. Typically, what happens in conventional multirotors, the rotor plane is always parallel to the XY plane of the body. Okay. Now this is what can be changed by mounting these rotors with the help of servos that can transform or that can actually change the rotor plane. But the moment you start changing the rotor plane, you are changing the direction in which the thrust is being generated, and hence through this you can actually in true sense achieve full actuation for the vehicle. So you can control your XYZ and the roll pitch, yaw angles, basically the position and the attitude angles independently.
So, like, do we have to have a non-fixed plane of the thrust?
It looks like. In fact, there is another arrangement. If you see, one is of course this when you where you can mount everything with respect to the with the help of a servo. If you see, there is another flying vehicle. I don't remember what they call it. So the rotors are essentially mounted on the 3 principal axes. So along x-axis there are 2 rotors, along y-axis there are 2 rotors, and then along z-axis there are 2 rotors fixed. Okay. Now because of this arrangement also, they can achieve this 6 degrees of freedom. So what is important to put is the just one rotor plane which is not aligned with the body's XY plane.
So basically, anti-parallel alignment of both in the 3 principal axes.
Not exactly anti-parallel. I mean, the rotor plane should be somehow be able to have the rotor plane out of the this one.
Okay, thank you.
Any other question? Yeah.
The question is asked by a student. How can an active guidance system for airborne drones or missiles be implemented using microcontrollers, microprocessors, and embedded systems? Additionally, what are the latest technological advancements in these areas that could further enhance such systems, particularly in defense applications?
Yeah, so I'm not an expert on guidance, so I really do not have any idea on this. So I'll not be the proper person to answer this. I'm sorry.
Okay, sir. Thank you.
Yeah, Yash, you can ask.
Hello.
Yes, you are not audible. Can you check? Anyone having questions? More questions to ask? Yes, you can go ahead.
Yes, sir. So, what are the real-time applications of flapping wing UAVs? And where they are used?
Flapping wing UAVs are popular for surveillance. Okay. Because they cannot take much of a load, at least what I've seen with the systems that have been developed at IIT Kanpur. So they cannot take much of a load, but they can take cameras. So they can be used for surveillance, and they have this nice camouflage that they can achieve. So you can perch on it. The best part is you can perch. Okay, it can be a tree branch, it can be a wire, and you can hold your position there and monitor the area. Plus they are energy efficient, So when I talked to the professor who had developed, he said that it is energy efficient. So for the same amount of battery, it can fly longer, and hence you can cover larger areas as well. Okay. So there are
Yeah.
practical applications mostly in terms of surveillance. Okay, surveillance monitoring. So it can be surveying commercial property or surveying an ongoing project, monitoring an ongoing project, and so on.
Thank you, sir.
Any other question? Yash, are you there? Okay, you can ask Akhilesh Kumar.
Yeah, hello sir. Actually, I have a doubt that the drones are becoming bulky and having a very much weight. So it is possible that a human also can travel with using these drones and all in future.
Can you repeat it, please?
Actually, the drones
Are
are
you
becoming.
talking of human transport using drones?
Yeah, exactly.
So this idea of air taxi is coming up. You have seen a lot of companies really going into it, right? So yes, people are looking into those things where they can transport human from one place to another to these unmanned vehicles. That might come up in future, but then because you are transporting a life, which means it has to have much more safety and stringent safety requirements as compared to uh, other flying vehicles. Of course, every flying vehicle has a stringent safety requirement, but since you are carrying something on board, you have to the requirement becomes more stringent so that the human life on board is not harmed. So it might take time, but of course it will come up. There are cases, study cases, and there are companies which are actually building such drones.
Okay, sir. Thank you.
Okay, you can ask.
So this is not regarding the drone architecture. I was just going to ask a simple question that are there any regulations or like restrictions regarding flying or operating a drone
Yeah,
in
that's a
India?
good question. So I think I'll request one of my colleagues sometimes, if you guys are interested, to give you some overview on the regulations for drones. So FAA has their own regulations. DGCA has come up with regulations as far as there are regulations. So for beyond a certain size, you need to have first of all, pilots have to have license. Okay, you need to have your drones registered. So it's same as registering any vehicle. Okay, you'll get a number against it. When you fly, you have to give your flight path plans, and you cannot fly in restricted airspace. There are a lot of guidelines that has come up. So if you want a detailed session on it, I think I can find out from my colleague if he can, and if you guys are interested, we can
Yeah,
schedule.
it was mainly because if we want to test or
Yes,
configure
yes, yes.
anything.
So uh, um, I think they are planning to come up with this central test areas, which basically would have been certified that yes, you can test drones of so and so specifications in these areas and all. But there are regulations that are coming up. They are being continuously revised as and when we are learning things with the number of drones increasing in the sky.
Thank you, sir.
So there's one question in the chat. Yash Tiwari is asking, how can we use drone technology for real world problems, and how is drone technology being applied in industry like agriculture and logistics?
Okay, so agriculture, there is a nice, if you go to the, I didn't know this, there is a program like this being launched by government. The government of India has this program called Drone DD, okay, wherein the women from the village who are basically from farming background are being trained to fly agricultural drones for basically spraying pesticides or fertilizers on their fields. Okay, I don't know what the scheme is exactly, but I had seen a report regarding it. So yes, and then there are this. For example, we had I think. Himachal Pradesh has this, the government has this apple farming corporation or something. I don't exactly remember the name. I think someone from there had approached one of our faculty members regarding some drone for plucking of apples and monitoring the health of apples and so on. So people are really looking into these things. There have been test cases where people have delivered medical supplies. There have been test cases where people have been delivering medical supplies, and in fact, governments are looking into that. If you remember, there was a dam collapse that had happened in Uttarakhand, I guess. So, Endure Air, I know that they had basically deployed one of the drones for monitoring those. Okay, at least I had a chat with the professor in charge who had found this company, and he had mentioned of it. I think it was in the news as well. Drones are being widely used for crowd monitoring, especially during Kumbh Mela and all. And the disaster management also, it is being used to assess the damage and locate survivors in the areas. So there are a lot of applications that are actually being a lot of real world applications where people are using. Okay, and it is picking up in India as well.
Hello, sir.
Yes.
Sir, मेरा कहना था कि
Professor, I have one
आपके
more
हिसाब से
question.
सबसे ज्यादा यूज
Actually,
सॉरी
I have huge interest in space science. So, how can we use drone technology in space science? Please guide.
Space science, even I have to also explore, but as there was one question on the use of Infinity on Mars by NASA, that is taking the drones to space now. Okay, so it's a nice area which I also want to explore. I have not explored yet, so I will not comment on it.
Okay, Professor. Thank you so much.
Yeah, good evening, sir.
Yeah.
Actually, what are the major constraints while designing a mini UAV or mini copter, and what do you think will be the applications?
Okay, so when you design anything, it depends first on the application. What is that you want to do it for? If it's just for flying for fun and you want to race, so usually racing drones are of the size of 150 to 250 because they become very agile, they are lightweight. Okay, and you can attain speeds of 100 kmph with suitable motors and propellers. Okay, so identify the application. For the application, you start writing down the specifications that you need for the drone, and it's an iterative process. It's basically a loop which finally converges to certain specification values. Once you have converged there, then you start assembling the drone. Okay, so it's not you build a drone and then look for the application. If you have an application, with respect to the application, you find out the specifications and then build the drone.
Okay, thank you.
Vipul, you were asking a question. Are you still there?
आपसे 2030 तक सबसे ज्यादा ड्रोन इंडस्ट्री किस फील्ड में सेक्टर में जाके ग्रो करेगी?
सेक्टर मतलब डू यू मीन कि कमर्शियल
सेक्टर जैसे कि जो भी ड्रोन के एप्लीकेशंस हैं,
हाँ,
उस सेक्टर की बात कर रही थी, मतलब जिस भी जगह पे हम ड्रोन यूज कर सकते हैं या फिर कोई नया एक अलग से सेक्टर बनाया जाएगा.
If you talk of India, drones have really not penetrated much. Okay. Now there are increasing demands in armed forces. There are increasing demands in business houses. There are increasing demands in government also. Okay. So if you see in the coming 5-6 years, almost everywhere there is a scope for increase in drones. And because of this scope, there are a lot of, if you see the number of companies that are actually manufacturing drones or supplying various components for the drones is increasing. Okay. So I would say that because drones are starting to penetrate various.
जैसे अपने इंडिया में फ्लाइट कंट्रोलर नहीं है
हाँ?
सर अपने इंडिया में फ्लाइट कंट्रोलर नहीं मैन्युफैक्चर होते हैं
नहीं है, फ्लाइट कंट्रोलर है, एक पुणे बेस्ड
जो इंडियन फ्लाइट कंट्रोलर्स हैं सर,
एक पुणे बेस्ड कंपनी फ्लाइट कंट्रोलर बनाया है. देयर इज अ स्टार्टअप फ्रॉम IIT दिल्ली हु आर मेकिंग फ्लाइट कंट्रोलर्स. Then I think Endurair has also made a flight controller, and I think there is one more startup also who has made a flight controller, and they are going for manufacturing. I mean, they are going for a design of wheel grade flight controller. India, mein, there are people who are manufacturing flight controllers.
यस सर. Okay, sir.
Okay, so I would like to express my sincere gratitude to Sir for taking the time to conduct this enlightening workshop. His passion for drone technology truly shines through, and we are fortunate to have had the opportunity to learn directly from someone who is deeply involved in advancing this field. Sir's ability to break down complex concepts and present them in an engaging way has made today's session incredibly valuable for all of us. We appreciate his willingness to share his insights and expertise, making this a truly enriching experience.
Thank you for inviting me. And this was a talk, so I might have made some mistakes. So if you look at any mistakes in the talk or if you have any comments, please feel free to drop me an email or help me correcting the same and add to my knowledge. I had a nice time engaging with you all. Hope you have a nice holidays. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir, for coming.
Thank you, sir, for your valuable time. We can conclude the session officially. Thank you all for participation.
Thank you, sir.
Thank you, sir.